Go ahead.
I don't think that we will go through an introduction of all of the participants, right? I see there's like 53 people here, so I think that will take up an hour by itself. So I think we can forego the introduction, so we can jump right into the session. So I'll try to share my screen with you and take it from there. So give me a minute so I can find my things and we can start. Okay, so okay, so you have to give me the right to share my screen because I can't see right now that I can do that.
Yeah, Abasud, can you help in that? Because you initiate the meeting. Abasud, can...
Yes, yes, I will do it. Just a minute, please. Dr. Christos.
Yes.
I invite you with your email.
Yes.
Are you enter with the same emails or from other?
Yes, I used the invitation that you sent me.
Can you give him the control?
Okay, I will.
Can you request Doctor the control so he can give it to you? I think there is an icon
Okay,
says
now I
request
can share.
control.
No, I have it now. So.
Now it's good?
Okay. Yeah, it's all right.
A representer now.
So can you see my screen?
Yes, but we need to do display.
Yes,
can you display it? Display.
Display, what do you mean?
Enlarge it.
No, there is a newer screen. Where is it? Down, you will find, display mode.
Or just F5.
F5, yes.
It is correct, Dr. Christos, where you have pointed.
Yeah, I got it. So now can you, it wasn't working for some reason, but F5 did it. So I think that's, you can see the screen now, right?
Slideshow, go.
It's the same. It's the same.
You go to slideshow.
Next to the 80%, you see the icon?
On my screen?
Down. Yes, down.
Yes,
I
down.
have a slideshow already.
Yes.
But you cannot see the slideshow.
Yeah. No,
it means you selected the wrong screen. If you reshare again.
How about now?
Yes, now good.
Now it's good.
Excellent.
So now you can see the slideshow?
Yes.
Yes.
Okay?
Excellent.
Okay, so apparently you can see the slideshow, but I can't, but it's all right. I guess I'll manage somehow. Let me see. How about now?
It's the same. Yes, good.
We can see.
Can you see your slide?
I can see my slide.
Excellent.
All right, then. So as I've said, and we've been told, we are looking at the GulfMed Peer Reviewers Qualification Scheme Training workshop. I'm calling this a survey of measurement uncertainty, method verification, and ensuring the validity of results. So let me just I don't know. I can't move to the next slide now. Oh, okay. It takes some time. Can you see the next slide? Can you see
Yes.
the slide now?
Yes, day one, day two. Yeah.
The training program outline, how I'm planning to work over the next two days. So today I'm going to discuss about measurement error and uncertainty. I will review a little bit about the math and the statistics which is used in uncertainty estimation. Talk about random variables and distributions, normal distribution, the way that we measure, or we actually estimate measurement uncertainty, the two methods that are available to us according to the methodology of the GUM. I am going to be a little bit qualitative to begin with about these subjects, and then I will go into the formal machinery, the tools that the GUM actually gives us so that we can estimate uncertainty, and finally take a look at some examples of uncertainty estimation using the tools of the GUM. Tomorrow, I will look at the requirements for selecting, verifying, and validating of methods. I will look at the distinction between method verification and method validation. The method verification in the new 17025 issue is mentioned much heavier, much more than in the previous version. So there's a big distinction which is made between these two activities. I will focus basically on a verification of methods, because in calibration, this is what is important. Validation is not that important, since the methods used in calibration laboratories are pretty much standard methods, and do not require a validation, whereas they usually do require a verification. Tomorrow, I will also talk about proficiency testing and the use of interlaboratory comparisons for this purpose. I will kind of go through how proficiency testing fits into the lab quality management system, how proficiency testing or comparisons should be selected, what are the requirements of accreditation bodies with regard to proficiency testing. I will give some examples from JAC and AAC from the region, from the Gulf region, and I will talk a little bit about how the results from proficiency testing or or ILCs are used in order to evaluate the performance of the participants in these exercises, and some specifics with regard to requirements of standards which might be used as transfer standards or artifacts in these exercises. Okay, so today is exclusively uncertainty, and I'll jump right into it. So what are the objectives of today's training? So I want to introduce the concepts of measurement error and uncertainty, as well as some basic statistics which are relevant to measurements. So I will keep this very, very simple and only introduce and use elementary statistics, very, very simple. I would like to acquaint participants with the terminology and the concepts that are included in basically the ISO GUM and all of the documents which have been produced by different organizations and NMIs which try to make the GUM more accessible to the end user. I will also introduce what I call the machinery for evaluating the measurement uncertainty as included in the GUM. But again, the GUM is a document which is relatively difficult to go through. So I will, this is obviously introductory, and we will be basically focusing on terminology and trying to explain what this terminology actually means. And then I will be using the GUM method to go through some simple examples, some elementary examples. And hopefully this will reinforce your understanding of these concepts. Okay, so my credentials, you've heard them already. I don't have to go through these again. There are two very nice documents which can be found on the web that deal with uncertainty. The first one is a beginner's guide to uncertainty of measurement, and just as the title says, it's a beginner's guide. So, but it's very well written, and even though it's already 23 years old, it's still very relevant to an introduction of uncertainty and uncertainty estimation. The second is the UCAS document, which is much more comprehensive and not that elementary, but it has all of the details necessary in order for someone to do serious uncertainty estimation and to use it in order to make decisions about the quality of the measurements that one is looking at. So both of these are available, as I said, on the internet, and if you don't already have them, you can find them very easily. I will basically be following this beginner's guide in today's introduction for about 2/3 of my talk, and the last part of the talk will be mostly from the more advanced document, the UCAS document. There's kind of a lag in my computer. I don't know why exactly. Oh no. Okay.
It's technology uncertainty.
Yeah, technology uncertainty for sure. So then let's look at what might be some the motivations of why one has to actually determine this thing which is called a measurement uncertainty. So these concepts, the idea of uncertainty, which is associated with a measurement, are fairly old to economics. They've been used from the 40s already, so they're like 70 years old. For metrology, for the area of metrology, which is related to economics in one way or another, they're relatively new. It's been more than 20 years that the idea of uncertainty has been introduced and used routinely in calibration and in calibration lab and metrology lab operations. And the reason why uncertainty is important, especially if someone is talking about an advanced economy which produces high-value products, is that someone wants to control the features of the products that are being produced. And in fact, if someone can estimate how certain they are about the measurements which are used in order to control these features, then the decision of whether these products are as intended encompasses much less risk than if uncertainty is not known, if there's no uncertainty estimation. So if someone wants to understand or control a manufacturing process, then someone needs to have measurements which have an associated uncertainty with them, so they could be used in whatever decision-making process is involved within this manufacturing process. And obviously, in an industrial environment, in a manufacturing environment, wrong decisions lead to increased costs. So you have to have a grip on how well you can make decisions with regard to the manufacturing process. And uncertainty gives you this added capability of making decisions with less risk. So in general, decisions that are made within the manufacturing process will have economic consequences. Okay. First of all, the decisions which are based on measurements cost money and time. And the management of the risk of making decisions can be done through an uncertainty evaluation. So the consequence of this is that risk can be managed by a measurement uncertainty analysis. A decision is based on cost analysis and hence is a matter of business economics, and bad decisions cost money, as I've been saying. So economically optimal decisions balance whatever the costs might be through uncertainty. So this idea of measurement uncertainty, the fact that decisions are based on measurements that are made, and the fact that measurements have an uncertainty, and uncertainty can be used in order to optimize decision-making processes, is central, either in a business or in a manufacturing environment. For us as metrologists, the manufacturing environment is basically the calibration lab, and even though it's not a product that we're actually manufacturing, we are producing something, and this something is a calibration certificate. So if we have an uncertainty associated with our measurements, then the validity of this calibration certificate that's produced through measurements, through calibration measurements, is enhanced. So I've been using the word measurement, so let me try to get a little bit more technical of what is meant when we say that we measure something. So whenever we measure something, we want to determine a property of this object or thing that we are measuring. So it might be that we want to know how heavy something is, or how hot or how long something is. And measurements are always made using some kind of an instrument. And the end result of a measurement is the assignment of a number to that property that we are actually trying to measure. Okay. This number is basically made up of two parts. It has a numerical value and it has a unit. So when we measure length, for example, we say, I don't know, 2-3 meters. So there's a number which tells us how long something is, but there's also something else which tells us, which gives us the concept of what this number actually means, and that's the unit of measurement. So a big part of metrology has to do with this unit of measurement, and its definition and its realization, and how this unit can be used by the end user in a uniform and systematic way. So I won't go into the details of this, because this is kind of another subject, and it has to do with traceability, and it has to do with the system of units of measurement, the SI system, which is today's international system of units. But the end result of a measurement is really a number and a unit. And today, in order for us to have measurements which are comparable from place to place all over the world, we have to use a uniform measurement system, and that's the International System of Units. So what would not be a measurement? So comparing two things is typically not a measurement. So comparing two pieces of string, for example, just by looking at them, okay, that is not a measurement. So you have to have numbers and units assigned to a particular property in order for us to be talking about a measurement. Counting is also typically not a measurement, okay? And a test is not really a measurement. Tests are used to decide on pass or fail with regard to something, with regard to a property. Even though, so a test per se is not a measurement, even though measurements may be used in a test in order to make this decision about a pass or fail, or yes or no, with regard to whatever we are interested in determining. Okay, well, if a measurement is the assignment of a number and a unit to a property of an object, then what is an uncertainty? So the way that we look at uncertainty today, nowadays, is that uncertainty represents our state of knowledge with regard to a measurement result. And when we say the state of knowledge, we basically mean the margin of doubt that we have about the measurement result. Obviously, so we know that even if we make measurements with a very accurate measuring device, because of many influences which are not controllable during this measurement, there is always some doubt regarding the result of this measurement. So this margin of doubt associated with measurements that we make with measuring devices, from the simplest to very, very complex ones, it doesn't really matter, This is what constitutes the uncertainty of the measurement. We should also keep in mind that the margin of doubt becomes smaller and smaller as the amount of information with regard to the measurement that we're making increases. So as new information is made available with regard to our measurement, then the margin of doubt becomes, and hence the uncertainty becomes smaller. So one can say that uncertainty and information are also related, and in fact, in advanced methods of determining uncertainty, the information content is very, very relevant to how this might be done. Of course, I'm not going to be talking about this today. Okay, so uncertainty then is the margin of doubt about a measurement. So what is not considered an uncertainty? So human error, as it's called, blunders or spurious errors are not considered an uncertainty, okay, but are pretty much considered a loss of what is called statistical control of the measurement process. So that means, in other words, that something is not functioning in this case as it is expected to be functioning within the limits that it's expected to be operating. So human error or blunders or spurious error are not considered to be an uncertainty. Tolerances per se are not uncertainties also. Tolerances are acceptance limits and are chosen for a particular process or a product. We'll see that in many instances, a tolerance can be used in order to determine an uncertainty, but per se, it's not an uncertainty, as specifications are not also. So a specification tells you what you can expect from a product, or a measurement device in our case, but they can be used in order to estimate uncertainties, but again, they are not what is called an uncertainty. Okay, well, let's see how we can quantify this margin of doubt. So in order to do this, there are two things that are necessary. So in order to quantify this margin of doubt, we have to know how large the margin of doubt is, okay? And we have to know what the so-called level of confidence is, or how much, how probable it is that this quantification of this uncertainty actually encompasses this margin of doubt. So the question of how large the margin of doubt is dealt with by assigning an interval, okay? And the question of how much doubt we have is accounted for by assigning a level of confidence or a probability to this interval. So, for example, when we say that we've measured the length of something to be 20 centimeters plus or minus 1 centimeter, that 1 centimeter is this margin of doubt quantified in units of length. In order to make this statement concrete, though, we have to associate with it a level of confidence also. And typically, in calibration, we associate a level of confidence of 95%, which means that we are sure that the actual length of whatever we are measuring is within a range of plus or minus 1 centimeter from the value that we have measured, the 20 centimeters. So the actual length will be somewhere between 19 and 21 centimeters with a probability of 95%. So this is a complete uncertainty statement. And again, it has two qualities. One is an interval within which we expect to find the true value of whatever we are measuring. And the second characteristic is a probability. So how certain are we that the true value is within this interval? Well, that's the so-called level of confidence, and typically it's 95% when we're talking about calibrations and calibration and the output of calibrations, which is the calibration certificate. So this is very central. It's a very central idea of what exactly measurement uncertainty is. Again, it's an interval centered on whatever measurement we have made, within which we expect with a large probability the true value to actually lie. Okay, we don't know exactly the true value because there's always an amount of fuzziness in any measurement, but we can with high probability assign an interval within which we expect this true value to actually lie. Okay, so if that is uncertainty, we saw that uncertainty is central to the idea of decision making, and as I said, it's been used in economics for a long time now, and for a relatively long time, it's being used with regard to assessing whether something is within some tolerance or within specifications. So what might, if I try to categorize the different benefits of uncertainty evaluation or measurement uncertainty evaluation, then it's very much relevant to what is called measurement traceability. Why? Because the idea of traceability includes the idea of uncertainty. So if you have seen the definition of traceability, you will remember that it's basically a chain of interrelated measurements. So in simple layman terms, no measurement is unaccounted for. All measurements should be tied down to other measurements until we reach the actual definition of the particular unit that of the quantity that we are measuring. Now, within this definition of traceability is the idea that when we're creating this chain of comparisons, of comparison measurements, this chain should be layered, and each layer should have uncertainties. As we go down this chain, the uncertainty should be, or actually I should say up this chain, the uncertainty should be smaller and smaller and smaller until we reach this defining point of the unit that's being used. So within the idea of traceability is the notion of uncertainty also. And that's why in calibration certificates, both of these statements, traceability and uncertainty, are central and equally important with the actual measurement results, the calibration measurement results. Uncertainty is important when we're talking about selecting the right instrument in order to perform our measurement. So, for example, we might be looking at a calibration where the reference should have a 4-to-1 ratio. Actually, the device being calibrated should have a 4-to-1 tolerance to uncertainty ratio. So this ratio tells me how many times better the characteristics of the reference have to be with regard to the device that I'm actually calibrating. An example is a 4-to-1 ratio. A typical rule of thumb is that the reference standard should be at least 3 times better with regard to its measurement characteristics than the device that it's being calibrating, that it's being used to calibrate. Nowadays, uncertainty is being used extensively in order to formalize this decision-making process with regard to measurements. So it's being used in order to optimize decision rules. What do I mean by that? Up to very recently, it was enough to say that a measurement result is within some tolerance limits or within some specification limits. Nowadays, with the advent, let's say, of uncertainty and its use with measurements, the decision rule has become such that it gives much higher reliability to whatever the result of this decision is, because besides the use of tolerances and specifications, uncertainty is also incorporated, and this increases the reliability of the decision by decreasing the risk that we have a false accept or a false reject decision being made. And another benefit is because we said that decision making is very much related to the cost of the production of the manufacturing of something, either a product or a service or a measurement result. So the benefit of an uncertainty evaluation is that the quantification of the uncertainty lets me dig deeper into my measurement and identify the sources of whatever the reason of a large uncertainty and thus a large question, a large doubt with regard to my measurement result might be. So uncertainty was recognized to be very important a long time ago, almost 50 years ago. Back in the 80s, the BIPM did a lot of work with regard to uncertainty, and all of this work was of a scientific nature, of course, and it culminated in the 90s to what we call today the Guide to the Expression of Uncertainty in Measurement, or otherwise the GUM. So the GUM is a method, is basically a document which is used to standardize uncertainty estimation and uncertainty evaluation. Okay, it's internationally accepted. And it's used by all NMIs, the National Metrology Institutes. It's used by all ISO 17025 accredited calibration labs, no matter which the accreditation body might be. And it's used by all modern organizations which are involved in standardization. So it's an omnipresent and all-permeating document which deals with uncertainty estimation and standardizes the methods that are available to us in order to estimate uncertainty.
Sorry, doctor. Are you changing the slides because we are stuck on the same the slide on the expression of measurement uncertainty with the 20 centimeter plus or minus 1? Did you change the slides?
I am
Yes,
changing the slides.
No, we
yes.
have we have the same slide the doctor have. Maybe
We have the
Yes.
same slide. Yeah.
I
No,
think
we
the
have-
like with you,
Yeah,
Dr. Arib, we are
Yes.
on slide 14 right now.
So it's with me. Okay, sorry. Yeah.
Okay. 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 So nowadays, this document, the GUM, is available under different names. ISO has published this as Guide 98-3. Actually, there are many parts to it today. I should go back one step. But this started out back in 1995. It was made up of one part. Today, it has, I think, 5 different parts because the use of uncertainty and the way that uncertainty is estimated is becoming more important in many different areas of measurement. So nowadays, there's a GUM, which is what is called the mainstream GUM. There is a guide that has to do with a different way of estimating uncertainties using numerical simulations, in particular Monte Carlo simulations, in order to determine an uncertainty, actually a probability density, and from that an uncertainty value for a particular measurement. There's a part that has to do with multiple input and multiple output systems to determine the uncertainty, and there's another part that has to do with the use of uncertainty in conformity assessment and in decision making. So I don't think that I missed something. So it's been enlarged and enriched over the years since 1995, when it was first introduced as a standard. It's available either through ISO, as I said, as ISO Guide 98-3, and this is, again, the mainstream GUM. It's also available for free download. All of these different parts to the GUM are available for download from the BIPM. And also NIST has its rendition of this document, which is available again freely for downloading. So the GUM is like, let's say, the holy book of metrology, of measurement uncertainty. And however, it is difficult in many instances to interpret, and that's why there are so many interpretive documents and more easily read, let's say, documents which are used by different organizations. But all of these are based on the content of the GUM. So pretty much nowadays, all uncertainty estimation is traced back to the guide to the expression of uncertainty in measurements. Okay, I'm not sure whether some of this terminology is known to you. I'm assuming that I'm talking to an audience which is fairly new to the area of calibration and of uncertainty and of metrology. So just so that we have a common language, I will go through some basic terminology before moving on to the actual uncertainty estimation content. So first of all, I've been using the word calibration, and I want to make clear with what is meant by calibration. So whenever we speak of calibration, we are talking about a comparison of an instrument against a reference or standard to find errors in the values indicated by the instrument. So the output of a calibration are differences between a reference standard and an instrument indication. And these differences are what are called errors or deviations of the indication of the instrument with respect to the reference. In some cases, not in mechanical quantities, not in physical metrology per se, but in chemical metrology, calibration assigns a relationship between the input and output of an instrument. So in chemistry, they talk about calibration curves for titration or whatever. Okay. So I'm not going to be looking at calibration from that point of view. I'm looking at it from physical metrology, where basically we have a clear comparison between the indications of two instruments, or the indication of an instrument and an artifact. The next term that is important is a very special word which you'll only find in metrology, really, and it's the word measurand. So a measurand is the particular quantity which is subject to measurement, or it's a set of specifications. Okay, so when I started out in metrology, I always thought that a measurand is basically the quantity that is being measured. So, for example, I started out in mass, and I thought that a measurand is mass, the mass of an object, just as in physics, for example. However, the measurand is as detailed as someone wants it to be. So a measurand is what I just mentioned, the mass of an object. Another measurand is the mass of an object at an air density of 1.2 degrees, 1.2 kilograms per meters cubed, and a temperature of 20 degrees. Okay, and even a different measurand is the mass of an object measured at an air density of 1.2 kilograms per meters cubed at a temperature of 20 degrees using a weighing balance. Okay, all of these things measure the same physical quantity, the mass, but the measurand is different. So the measurand does not coincide exactly with the physical quantity that's being measured, but it's the physical quantity plus a set of rules or specifications that are assigned to the way that this physical quantity will be actually determined. Okay, so it's a little bit more complex, and because it's a little bit more complex, the measurand itself is in many cases a source of measurement uncertainty. So if a measurand is not defined completely for the particular instance, okay, that it's being used, then there might be this might contribute to the uncertainty of the measurement of the particular physical quantity. Okay, I hope that this distinction is very much clear in your minds, that it's not just mass length or whatever. It's mass length measured at specific conditions, possibly with specific instruments, possibly with a specific method, and so on and so forth.
Doctor, you mean the measurand, it's a measurement with rules?
Yes, pretty much that, yes. I would say rules or specifications, okay? And depending on the accuracy of the particular measurement, the accuracy with which something needs to be determined, the measurement could be very simple or it could be very, very complex. If someone does not correctly account for this complexity, then the uncertainty with which this measurement is determined increases. Okay. Okay, not central to the idea of uncertainty, but related, especially nowadays, is conformance or non-conformance with tolerances or specifications. So we say that something is conforming when at least one true value lies within or on the boundary of a stated tolerance interval. And something is non-conforming when all true values lie outside the boundary of a stated tolerance interval. Now, in between, there's a whole bunch of other possibilities, and that's why uncertainty is important, because it can be used, uncertainty can be used in order to distinguish between all of these other possibilities, between clearly conforming because everything is within, okay, and clearly non-conforming because everything is outside of these tolerance intervals. So another word which is used very much, very often by anyone working with measurements is accuracy. And this is a strange word because what is meant by accuracy is the closeness of the agreement between the result of a measurement and a knowable true value of the measurement. And this is where the difficulties, the conceptual difficulties start to arise, because if someone knows the true value, then why is someone actually performing a measurement to determine it? So it's kind of like a cyclic argument here. So one question is what we mean by a true value here. It's not the absolute true value, but it might be the true, what we consider to be a true value, conventionally, let's say. Okay. At any rate, the accuracy is the closeness between what we measure and what we consider to be a true value of the measurement. Okay, it's a qualitative concept. It should be avoided, even though we, as I said, we use it. I use it also when I discuss with people measurements in the laboratory. But we should try to keep clear of it as much as possible, and instead of accuracy, speak about uncertainty, which is basically a quantitative statement of accuracy. I should also point out the distinction between accuracy and precision, okay? So even though in everyday language we might be using them interchangeably, they have two distinct meanings, okay? So accuracy is the closeness between two measurement results, or a measurement result and what is considered the true value. Precision is pretty much related to how repeatable something is. So we say that something is precise if its measurement is highly repeatable. And that has to do with, well, I won't go into more detail, but just keep in mind that accuracy and precision really mean two separate things. Okay, and now the most important word, the word of the day, uncertainty of a measurement. So what is uncertainty? It's a parameter which is associated with a result of a measurement and characterizes the spread of the values that could be reasonably attributed to the measurement. So this goes back to the idea of uncertainty being an interval. Okay. So you see here, this says again that this parameter uncertainty characterizes the spread, the dispersion or the spread. So it characterizes an interval within which the true value is expected to be found. Okay. When someone says the spread that can be reasonably attributed to the measurement, that's basically what is meant. An interval within which, with high probability, we expect to find the true value. So there are some questions that might arise with this definition. There's the question of what is meant by reasonable values, okay? In essence, reasonableness allows expert judgment in addition to experimental data. So as we will see later on, the way that uncertainty is estimated allows expert judgment to be used besides actual measurements that are done in order to determine this quantity, this uncertainty. So, okay. We see that uncertainty is a parameter, okay? And a parameter means that it's a number, so it's a positive number. It's not an interval, and it's not a probability distribution. It's a number. So when we write down uncertainty, it's not 100% correct to say plus or minus so much. So for length, plus or minus 5 microns or micrometers. The correct way is to just say that the uncertainty is 5 micrometers. This is something that I see very often, this mistake being made on calibration certificates produced by calibration labs. So how are measurement results stated when someone wants to include the uncertainty? Well, then you have to say that the actual true value is equal to whatever I've measured plus or minus the uncertainty. Okay, this plus or minus is called the interval, is called a coverage interval, and it's equal to twice the uncertainty, and this is the interval which quantifies the margin of doubt about the measurement that we have made. Uncertainty also is an attribute of a measurement result. So it's associated with a measurement result, not an instrument. Instruments do not have uncertainty. Okay. I hear this when I discuss with people from calibration labs. So we have to keep it clear in our minds that the measurement result has an uncertainty because of the different influences during the measurement. The instrument might be one contribution to the uncertainty, but instruments per se do not have uncertainty associated with them. They have specifications, and because of the specifications, they might influence the measurement result in one way or another, and thus produce uncertainty in the measurement result. Okay, I want to make a distinction between measurement uncertainty, okay, and measurement error. So the uncertainty, the measurement uncertainty is basically a parameter which designates what is called, as I said, a coverage interval, okay, an interval within which we expect the true value to lie. On the other hand, measurement error is a number, okay? It has no probabilistic characteristics associated with it. It's just a number, and it's defined as the difference between the indication of an instrument and the true value. So again here, the question is, what is this true value? Okay, well, it's what might be considered a conventional true value. So that would be then the measurement value as realized by whatever we are using as a reference standard. Okay, so in every comparison of this sort, what we consider as a true value is whatever the indication of my reference standard or my reference artifact might be. Okay, so the error is defined really as the difference, and in this way only, as the difference between the indication of an instrument and the indication of a reference standard. Okay, obviously this is related to the correction, and the correction that I have to make to the indication of an instrument is the negative of the error. So error and correction have a difference of a sign between them. Okay, if I know the error, then I know the correction that I have to provide to the indications of my instrument. Errors, obviously, because they are numbers, they could be positive or negative. Uncertainties, we said, are positive numbers only. Yeah, so we can only determine, the last point says that we can only determine errors when we have an estimate of the true value. And as I said, this estimate of the true value is whatever is the value of whatever we are using as a reference. So when we have calibrated objects, okay, which are being used as references, then those are the best realizations of the true value of the measurement. And we are, when we're comparing to find errors, we're comparing with these true values within quotes.
Dr. Christos?
Yes.
If you excuse me, we're gonna break at 10:30. Is it okay?
10:30. Well, I'm trying to see what my next slide is, but for some reason now it's not moving along. Okay, so I still have a few. Yeah. I guess we can do that. So if I were to give a graphical view of what I've been talking about, then this is what the graph that I would be showing you. So on here are all of the definitions that I've been discussing with regard to uncertainty and errors and so on and so forth. So you see here my measurement, my measured value, which is equal to y, and it's central. I don't know if you can see the cursor. Can you? Can you see the cursor?
Yes, doctor, yes.
Okay, so my measured value is over here, okay? And because I'm a good metrologist, I've also estimated some uncertainty with this measured value, and this uncertainty is this much. And this uncertainty then creates bounds within which I expect to find my actual true value. And these bounds are from whatever I've measured plus the uncertainty to whatever I measured minus the uncertainty. So then there's a high chance that the true value is somewhere within this rectangle here. Well, actually on this line, I should say. Okay, within this interval. The fact that I'm talking about a high chance, I'm talking about a probability, lets me draw this probability distribution which shows this chance. It says that Well, if the assumption is that the measurements follow what is called a normal distribution, then this is what the probability will look like of finding the value somewhere in here. The probability is higher to find it close to what I've measured. And as I go away, it becomes smaller and smaller. It doesn't become zero, that the probability is outside actually of this interval that I defined around the value that I have measured. So there's a slight chance, in fact, if I'm talking about a confidence of 95% or a probability of 95% approximately of the true value being somewhere within here, then there's about 5% chance that the true value will actually be on the wings of this distribution somewhere out here. Okay. So there's a higher probability for it to be found somewhere around close to what I've measured, but there's some probability that it's all the way even up to the edges here. Okay. So this gives you the idea of why uncertainty has a probabilistic or a statistical nature associated with it. Whereas the error would just be a difference between what I have measured and what the actual true value is. Now, again, cyclic argument, because if I know what the actual true value is, well, I don't need to measure it. So what do I mean here by true value? Well, I mean the closest thing that I have to the true value. Well, what is this closest thing? It's a calibrated reference standard. So the difference between the indication, the difference between whatever I am measuring and what the reference standard is measuring might be considered to be the error in this particular situation. The error or bias. In some cases, the word bias is used. Okay, with regard to errors now, we have, broadly speaking, two types of errors. We have what are called random errors and systematic errors. So what is an example of a random error? So if I measure a gauge block twice with a caliper, a measuring device, I will get two different measurement results and two different errors. So when repeated measurements yield a distribution of errors for whatever I am measuring for the measurand, then I talk about random errors. So random errors, in other words, are what the word says, random. They are not stable. They vary from time to time under the same conditions of measurement. Okay. On the other hand, as I said, we can have systematic errors, which produce a measurement bias. Okay. And what are systematic errors? They are the component of a measurement error that in replicate measurement remains constant or varies in a predictable manner. So in the graph here, you see that there's a bias, a systematic component to the error, and there's a random component also, because all of those red points are not on that specific dashed line, but they fluctuate around that dashed line. So that fluctuation around that dashed line, which is let's say the value that I have measured every time. So I have repeated measurements of a quantity. My most probable measurement is that dashed line, and the individual measurements, every time I repeat them under the same conditions, they fluctuate around that dashed line. The difference between that dashed line and zero constitutes a bias in my measurement, and because this is constant, it's called a systematic error. Okay, so in this case we have a small random error because all of the points fluctuate very closely to that dashed line, but there's a relatively large difference between what I've measured and the 0 value there, which is the true value. So there's a relatively large bias. So there's a relatively large systematic error. So two types of errors broadly, two categories. Random, it changes under repeated measurements under the same conditions. Systematic, it doesn't change. It remains constant. So when we are calibrating something, we are basically trying to determine this systematic error, okay? And the calibration, the output of a calibration is the production of a correction or a correction factor to account for it, to account for the systematic error, okay? So systematic errors can be corrected for. One way is through calibration, okay? However, because a calibration is also a measurement, there's an uncertainty associated with it. So even though I can correct for systematic error, there's still some leftover, some residual, which I cannot determine, and that constitutes an uncertainty. Okay? So in general, the small residual systematic error, after all corrections have been made, is the uncertainty that is left over after I make corrections for systematic error. So then if I were to try to summarize the differences between systematic and random measurement error and how each one of these is handled and how it fits in with what I'm speaking about today with uncertainty, then I would have a picture of this sort, okay? So again, I make a measurement. The measurement has some error associated with it. This error is broadly categorized as having a systematic component and a random component, okay? The random component I cannot do much about. I can try to estimate how much it is by using statistics and then include it in the measurement uncertainty. I cannot correct for the random component of measurement error. The systematic error then could have two components associated with it: a known systematic error and an unknown systematic error. The known systematic error is what I determine through a calibration, for example, okay? The unknown is what the calibration cannot account for, okay? So this unknown systematic error then should be included in the measurement uncertainty. Moving further down, this known systematic error, I can correct for, I can make a correction and produce my measurement result. However, as I said, even though I can correct for known systematic error, there's still some residual left over. And this residual also will constitute a measurement uncertainty. So at the end, my final measurement result will be what I've measured plus a correction, and my final uncertainty estimate will be composed of three parts, will be made up of three sources, let's say. A source which comes from the random measurement error, a source from the unknown systematic error for which I have not corrected, and a source of residual error, which is what is left over after correcting the indication of my instrument for the known systematic error. So yeah, this is I think a very clear picture of how error and measurement uncertainty are related. So obviously they're not the same. Uncertainty is a statistical or probability concept, whereas error is a number, really, a correction to the indications of my instrument, or the opposite of a correction to the indications of my instrument. Okay. So to finish up, this part of my presentation, so where the final question is, all right, so this is what uncertainty and what error is. So where do these uncertainty, where does the uncertainty come from? Okay, so what might be the different sources of errors which produce uncertainty in my measurement result? So this is not an exhaustive list here, obviously, but it's the most prevalent and the most obvious. So the measuring instrument itself is a source of measurement error. So if I use a measuring instrument to make a comparison between an unknown artifact, an unknown object, and a known object, then the measuring instrument itself is a source of errors and hence uncertainty. Okay, and that's because the instrument might have bias because of the way that it's manufactured. It could have effects because it's aging and because of wear, because it's drifting with time. So all of these issues are error sources due to the measuring instrument, and this is the component that we actually try to determine when we perform a calibration of something. So we try to determine what the contribution of the measuring instrument to the uncertainty of whatever it is meant to measure might be. The item that is being measured might contribute. So we have the instrument, which is used to make the measurement. The item that is being measured is might be another source of uncertainty, because, for example, this item might not be stable. So if we're talking about the volume of water that's contained in a vessel, then depending on how large the vessel is, the evaporation of the water inside this vessel might constitute a source of error and hence uncertainty. The measurement process itself, okay? So the measurement might be a difficult measurement to make, okay? So because of this inherent difficulty, there's uncertainty which is introduced. There might be imported uncertainties because of the calibration of instruments which are being used and in order to make measurements, and through their calibration, the result of the calibration has an associated uncertainty with it. The operator's skill might be a source of uncertainty, okay? So because skill and judgment play a role in many instruments. That's why the training of operators and technicians is a very, very important aspect of quality systems and uncertainty estimation. Sampling issues, the way that I sample things, okay? Is my sampling scheme, the sampling of the measurand, representative of the process that I am trying to assess? And the environment. So influences of the environment could produce errors, temperature, air pressure, humidity, and any other conditions, which lead to uncertain measurement results. So these are the most obvious contributions or influences, and this is where someone should start looking for sources of uncertainty in their measurement. Okay, I guess we can stop now for 15 minutes and continue afterwards. I don't know if there are any questions to what I've been talking about. I guess this is good as any point to ask. Are there any questions?
Well, Dr.
Okay.
Christos, it's obvious that the participant needs a break. So that's what we gonna do. But before that, we would like to register this memory by taking a group photo. So I would like to ask all the participants if they can open their camera. And my colleague Abdelillah is ready to take a group photo.
Okay.
Yes, Abdelillah, are you ready? Tell me. We will give you some time to
Yes.
the participant actually to prepare their self for the group photo.
Okay, I will take more than one.
That will
Be
be
ready, please.
excellent. I thought you are a professional in that. We need a very nice pictures for our participant
Inshallah.
with big smile.
Okay.
Wear your glasses, Omar. It'll be good.
With I will do my glass.
We didn't recognize you without glass.
Okay. Right now is good. I'm sorry that I'm not.
Okay.
As I've said, I was old. Tell me
Okay.
when you are.
Okay, it's done. It's done.
It's done. All you can
Yes.
see all the participants. Can you catch them?
No, no.
Not
Actually,
all.
I have nine screens only.
9 each screen or what?
9 screens.
I would like
Can be.
all of you just to open your camera. It's a good opportunity for us to see you.
بس سعود اهم شيء انا مبين ولا لا؟ انا من ضمن التسعه
أيوة.
هذيلا.
اي ما شاء الله موجود هذاك.
أحمد.
هذا اهم شيء.
Yes.
يا مرحبا يا مرحبا.
طيب.
ايش معك؟
Yeah.
يلا again.
Mhm.
Again be ready.
So you are getting more faces.
Okay.
Okay.
Thank you.
In this case, yes, I hope you enjoy your break. We will come back after 15 minutes. My colleague Abdelillah, can you put the counters? So it will be as an indicators
Okay.
to start again. Have your nice cup of coffee, Dr. Christos. Well done.
I will.
I think it's very, very interesting topics, and I think that I enjoy, learning a lot of issues related to the calibrations. Thank you very much for this very nice presentations.
My pleasure. My pleasure. So I'll see you in 15 minutes then, right?
Yes, that's right.
Okay. Okay. Thank you.
Dr. Christos, are you back?
Yes, yes, I am.
Thank you. I think just give 1 minute, then you can start, Dr. Christos.
Okay, let me try to
So-
find my presentation again. You might need to help me out on this. So can you see it?
Yes.
Yes.
Okay, good.
Doctor, can you display it?
You cannot
Same
see
as
it?
before. I see it, but it's not in the display mode.
It's not in the display mode. Oh. Let's see.
It's gonna be the same.
What did I do? Was it F5 or Control F5 or something?
F5.
Yeah, F5.
It's not doing anything.
No
Maybe you are
change.
sharing maybe you are sharing the wrong screen.
Try to share again.
Yeah, let me try it again. So what can you see now?
Dr. Christos, it's showing just the, it doesn't show in presentation mode. So maybe like before, next to where it says 80% down at the bottom, if you click that little presentation window, see if it
How
pops
about now?
up. I'll wait a second.
The same.
Yeah, same.
Well, I clicked on it.
Yeah, I
and
think,
it's,
but
on my computer, it changes the presentation. So I don't know what else to do.
Dr. Christos, if you have two monitors, probably you are showing the other one. So
Exactly.
try to reshare with the right screen.
Two monitors. I don't have to. I don't understand two monitors. I have a laptop. I don't understand where the second monitor is coming from.
Yeah.
When you click share, what there is multiple, types of screen that you would like to share, isn't it?
Yeah, there are.
Probably
Share
if
your
you
desk-
choose screen one or where it shows the
your
presenting mode.
It's got screen one. It says Microsoft Teams, and then it has my presentation. So I'm not quite sure why it's got what the screen one mean and what Microsoft Teams means. To be
Try
honest.
screen one. We will see if it's this one. If not, then the other one.
No, this is not one. No.
Okay,
not
this
one.
one, it's normal presentation. This is Teams. And no, where's the third one?
How about this?
No, it's the same.
Same meaning what? It's
Presentation.
It's not
It's not in presentation.
presentation, not on. Yes.
On
So if
Zoom.
you click down present mode next to the 80% in the toolbar.
yeah, it does it on my computer, but it apparently it doesn't do it for
the
you.
first icon. Oh, okay.
Maybe it's need time.
Now it's PowerPoint. It's basically showing the presentation mode on his view and then the other view on our view. Maybe I don't know if this will work, Dr. Christos, but if you do the Windows key and then hit P, so Windows key P, it'll bring up on the right hand side of your screen. It'll bring up where you can select duplicate.
Yeah.
So if you hit Windows key and P at the same time, it should allow you to select duplicate. There'll be like PC screen, duplicate, extend.
So what do
I'm
you
just
see
trying. Right now, I see your presentation, but not in a presentation format. Just the slides are on the left and the main slides in the middle. So maybe try clicking on that presentation mode window again, but next to the 80%.
في كل مجال.
How about now?
يعني على 6 ثانية.
Dr. Christos, if you can stop sharing, do first presentation mode, then try to share. Probably is based on the sequence.
دقائق ما تكتبوا.
Okay.
Stop sharing, Doctor.
Yeah,
he stopped.
do presentation mode first, then try to share.
Open the files and put it in the presentation mode.
So it's in presentation mode, but now it's in presentation mode. I cannot access.
No, you will find it. There is,
Yeah. The presentation mode will take the whole screen, so we cannot see now the.
So
Teams.
Engineer Omar, to catch the time, it's fine that he can present it the way
yes,
it is.
go ahead.
Yeah, no problem.
Yeah, no problem.
No problem. Let me. So I'll try to make it as large as possible. Which is this? Is this okay?
You are
Share
not
it.
sharing.
Share it.
Sorry.
Yeah, okay.
It will be okay.
was doing it previously. I don't know what happened now, but anyway.
That's technology.
Well, yeah.
Or, yeah, moment.
My computer is relatively old, so maybe that's an issue. I don't know. It's telling me time to get a new one. Anyway, so are there any questions with regard to what we were discussing?
Dr. Christas, you may right click on the ribbon up and just click on collapse the ribbons. Right click on the ribbon. Yeah, right click. Yeah, up in the ribbon itself, and then you have to have something. No, in the ribbon. It's a collapse. Minimize the ribbon. Minimize the ribbon.
Yeah.
Okay, that's fine. Okay, good.
All right. So, are there any questions? So the next thing, if there are no questions, that I would want to discuss is some basic statistics that is used in order to estimate uncertainty of measurement. So in essence, I want to talk about the average or arithmetic mean and the standard deviation of a set of numbers. So why would someone want to do a set of numbers? Because as the old saying goes, measure thrice, cut once. So to guard against gross mistakes or operator error, okay, it's wise to take at least three repetitions of a measurement. So obviously, the more repetitions that someone makes, it's a statistical fact that the closer that someone gets to the actual true, actual unknown true value. But you need, let's say, a rule of thumb is that you need at least three measurements in order to guard against gross errors in your measurement. Okay, so always keep that in mind because I've seen labs that they tend to do, especially in mass calibrations, they tend to do one or two repeats, and that's enough for them because OIML specifies a minimum number of repetitions necessary depending on the class of the weights that are being calibrated. But it's always a good idea to do at least three. Okay. So the items that I want to talk about is the average and the standard deviation of repeated measurements. I know that most of you know this stuff, but just that we have a common ground that we are looking at things from. Okay, so an average, or the arithmetic mean, gives you an estimate of the true value and is usually shown by a symbol with a bar above it, so X bar in this particular case. So if someone repeats a number of times a particular measurement, then this the results of this measurement are shown in this picture here as being dispersed on the horizontal line. So it's not expected that you will get the same result because of the influence of different factors during the measurement, which are not constant. So because of random errors. So the best way of determining what the actual measurement is then is to take the average or the arithmetic mean. Okay. The more measurements you take, as I said, the closer you get to what is called the true value, or what you can call the true value. If you were able to make infinite measurements, then you would find the true value, but obviously that's just an idealization. It's a mathematical construct. So in reality, you make a number of measurements. Keep in mind that the more measurements, the closer you are, because it's a fact of statistics. However, you should always keep in mind that performing more measurements takes extra effort, and you have diminishing returns. So a popular choice is 10 because it's a nice number to divide with and do calculations. Okay, so when you're doing repetitions, it's a good idea to do maybe 10 measurements. 20 would be better, 50 would be better, but you would see that the end result is on. It doesn't. The improvement doesn't increase proportionally with the effort that you're putting with regard to the number of repetitions. So there's always a fine line, and 10 is typically where someone draws this this line, because it's also a nice number, as I said. So when someone wants to find the best estimate of the true value in order to account for random errors, you do repeated measurements and you take the average or the arithmetic mean of these repeated measurements. So the best estimate then of these repeated measurements would be just the sum of what the outcome of each measurement is divided by the number of measurements, and that is the average. Okay, so the average is a nice little tool to determine the quote true value from your measurements, from your indications. And I think that everyone knows that there's an Excel function in order to do that. So if you're doing your calculations in Excel, then the function average actually calculates this this average value. So to make a long story short, summary, the best estimate of the value that you're measuring, of the measurand that you're trying to determine from repeated measurements, is the average of these repeated measurements. Well, as we saw, if you do repeated measurements, not all of them will give you the same result. So an indication of how good your measurement is the spread of these repeated measurements. And the spread is in general used to judge the quality of the set of measurements. And this spread is associated, we will see later on, with the uncertainty of measurement. Okay, roughly speaking, this spread can be estimated by two ways. One can decide to talk about the range between the highest and the lowest value. Okay, so that's one way of quantifying the spread. Another way of quantifying the spread is to calculate what is called its standard deviation. Okay, so what does this standard deviation tell me? It tells me what the how the different individual readings are placed with respect to the average that you have just calculated from these repeated measurements of a set of measurements. Okay, so one determines the best estimate of the measurand from repeated measurements by the average, and then you can determine how well you've performed your measurements through the standard deviation. So then that tells you how close any one of these measurements is to the best estimation that you have available of the actual value of the measurand, which is the average. Okay. Both of these are very, very important and are used to calculate, to determine uncertainty of measurements, of repeated measurements. So what does the standard deviation tell me? It tells me that roughly 2/3 of all of the readings, the repeated readings, will fall between plus or minus one standard deviation from the average. Okay, so And the standard deviation tells me that roughly 95% of all readings will fall within 2 standard deviations. So you have 2 methods of determining the spread, which shows you how well you've attempted to measure something. One is through the range, so it's the difference between the maximum value and the minimum value that you've determined. The other, which has a statistical interpretation to it, is the standard deviation. And the statistical interpretation is that roughly 2/3 of the readings will fall between plus or minus 1 standard deviation of the average, and roughly 95% of all readings will fall within 2 standard deviations from your average value. Okay, there is an underlying assumption here, and the assumption is that the values are actually, the measurements are actually distributed in a particular way. So as we will see, they should be following a normal or Gaussian distribution if the 2 above facts are actually to be observed, okay? So for other types of distributions, this roughly 2/3 and roughly 95% of all the readings doesn't apply. It really applies only to a normal or Gaussian distribution of the measurements, or the errors of the measurement. Same thing. Okay. The other thing that we should keep in mind is that we are actually sampling. So whenever we're performing repeated measurements, we're actually sampling from the population of all of the possible measurements. So actually what we're determining is what is called the estimated standard deviation from the sample of all of possible measurements. That's why this is typically symbolized by the letter S and not by the Greek letter sigma, which is reserved for the mathematical symbolism of the standard deviation of the population, which is really of an infinite number of readings. So the mathematics behind statistics talk about everything converging when you have a very large amount of readings. In reality, we're only sampling, we're taking a small number of measurements, 10, 5, whatever, and we're estimating these statistical indices, these numbers, okay? So we have an estimate of the standard deviation from the limited number of repetitions that we're performing, and obviously we have an estimate of the actual value of the measurand through the average, because again of the limited number of measurements that we are performing. As I said previously, the more the number of measurements, the closer my average and the standard the estimated standard deviation go to these mathematical constructs of the mean and the standard deviation. So this is more of a note than anything else. It doesn't really affect the way that that someone works, because we work only with a limited number of measurements, and that's the best that we can do. Okay, but I just wanted to make this distinction between the average and the standard deviation of the sample and of the population of measurements. So then the estimate of the dispersion of repeated measurements through the use of the standard deviation, the estimated or experimental standard deviation, is given by this expression here, which basically sums up the difference between the individual measurements from the average, squares them, and then adds them. Okay, so we're looking at the deviations of each individual measurement from the average but we're looking at the squares of these deviations, actually. So we're adding squares of deviations from the average here. And then we're dividing by the number of repeated measurements minus 1. This is called the number of degrees of freedom. And there's a reason why this is n minus 1 and not n, because already you've used up one of these degrees of freedom to calculate this average. So you have to take that away from here. And this is why this is n minus 1 instead of n. So if someone does this, then you're measuring the dispersion of each one of these numbers from this average, and the square root of it gives you the standard deviation. The quantity within the square root by itself is called the variance. So this thing in here under the square root is the variance. The square root of the variance is the standard deviation. There's an Excel function to calculate this, so you won't have to do this every time you want to determine what the standard deviation of a number of repeated measurements is. There's actually an assortment of Excel functions to do this, but the one that corresponds to this formula here is what I'm showing on this slide. So then this, the experimental standard deviation, shows me the dispersion of each individual measurement from the average. Now, we can also think about the standard deviation of the average or the mean. So if I take sets of n measurements and I calculate their averages, then the next question I might ask is, well, how are the averages dispersed around the actual true value? Well, this is given by the standard deviation of the mean, or the mean error, as it's called, and it's determined through the experimental standard deviation just by dividing it by the square root of the number of measurements. So if I divide this quantity here, my estimated or experimental standard deviation, by the square root of the number of measurements that make it up, then I determine the standard deviation of the mean. And this measures how well the average approximates the actual unknown true value.
Doctor, sorry.
Obviously, yes?
The n in the standard deviation and the standard deviation of the mean is the same n, because I see capital and...
Yeah, it's the same, sorry.
Yeah,
It's
okay, sorry. Okay.
So I'm talking about capital N number of measurements, okay?
Yeah, okay, thank you.
All right, so obviously the standard deviation of the mean or mean error is smaller than the experimental standard deviation. Okay, and why do I say obviously? Well, because this is made up of a number of measurements here. Okay, so each one of these values, the average, is made up of a number of measurements. So I expect that the distribution, or the dispersion of these numbers around the true value is smaller than the dispersion of one measurement around this average value. So in general, because I'm using more information, more input to determine this dispersion, its value is smaller than the experimental standard deviation. Okay, so just to see how this is done, I'm sure that most of you have know this, but just to bring back to your memory some things, maybe if it's a long time since you've done it. So let's say that I have a number of readings of a particular quantity, 10 readings specifically in this example, and I've calculated the average of these 10 readings to be a specific number. And my question is, what is the estimated standard deviation of these 10 readings? So You can either do it in Excel, you can do it by using a scientific calculator, okay? So depending on what type of calculator you have, the keys might have some symbol. Typically, there are two symbols on scientific calculators for standard deviation. One is S sub n or sigma sub n, and the other is sigma of sub n minus 1. This is the one that you should be using to do the calculation, because the sigma sub n calculates the standard deviation of the population. You're interested in the standard deviation of the sample of this particular sample of measurements that you have. If someone decides to do it in Excel, then someone might set up a spreadsheet which looks something like this. So in this column, I have all my individual measurements, 10. I calculate the average here through the average function, which Excel makes available to me. Okay, and in the column next to it, you see here, I have the difference of each one of these measurements from the average. So this difference can be positive or negative or 0. Okay, and in the column right next to that, I have the squares of these values. Okay, so this is a manual way of, actually it's an application of the formula that I showed you earlier. And down here is the sum of all of the numbers in this column. And since now I have the sum of the squares of the differences, if I divide by the number of measurements, by the degrees of freedom, which is 10 minus 1, 9, and take the square root, I will get this result for the standard deviation. If I just tell Excel to do the calculation with its standard deviation function, I get this result, and you see that they are identical. I have to point out here that Excel, in fact, uses a formula. If you go to the Excel help and see how it calculates the standard deviation, you'll see that it doesn't mention this formula here. It mentions a different formula by which it does its calculation, and that has to do with the computational aspects of the use of this formula in comparison to the one that Excel uses. So Excel uses a more robust, let's say, expression of standard deviation to do the calculation than this here, numerically robust, I mean. Okay, so don't be surprised if you see in the Excel help that the function that they're actually using to calculate the standard deviation is not what I just showed you. The end result is exactly the same. Any questions? Okay, that's good. Okay, well, I kind of hinted already. Well, I didn't hint. I said that there are different ways by which measurements are dispersed, or I should say repeated measurements are dispersed. Okay, one way is by following what is called a normal distribution. But there are other ways also with which these numbers can be dispersed. So when we're talking about the when we're talking about the dispersion of measurements, okay, we're talking about the way that they are distributed, and we're talking about the shape of the, if we can say that, the shape of the errors. So the spread of a set of values can take different forms, and these different forms that this spread can take are called probability distributions, roughly speaking. So on the left here, I have how the spread looks for a number of 10 repeated measurements, or it might look. And on the right-hand side, I have the corresponding probability distribution. So in this case, if measurements are distributed this way, the spread looks something like this. What's the characteristic? It looks like most of them are kind of bunched up in the center, but you still have some values at the far away from the center. And in fact, how far away? I mean, if you did more measurements, you'd probably find maybe after, I don't know, 100 measurements, you'd find also a measurement out here. So there's no definite limit within which you find all of the repeated measurements that you do. However, you do find most of them bunched up in the center and a few far away from the center. So this is typically the distribution which corresponds to a Gaussian or normal distribution. And if I were able to do a very, very large number of measurements and put them on a graph of the probability of occurrence with the result of the measurement, I would get a kind of a continuous function, which would look something like a bell curve like this. Okay, so you see over here I have the probability of occurrence, which means how many measurements from the total I have which show up here or anywhere along this line. So I would see that the ones that show up around this number are much more than the ones that showed up around here. So these are called the wings of the distribution, and this is called the center of the distribution. I don't want to go into more details with regard to this because I don't want to make this statistically complicated. I just want to note, and for you to understand that dispersion of measurements can take on different forms. Okay, so one form is what is called a Gaussian distribution, probability distribution. The other form is what is called a uniform or rectangular distribution. So what are the characteristics here? One characteristic is that there are definite bounds to where these numbers are distributed. I will never find any number past these bounds. And the second characteristic here is that there's no particular value which is more probable than any other. So these don't seem to be bunching up anywhere. They just pop up randomly within these two bounds. So these are characteristics of a uniform or rectangular probability distribution. Okay? So both of these are very, very important when we're estimating uncertainty. And maybe 90% of the uncertainty estimation is done by using these two types of probability distributions. Okay, so what should you take away from this slide is that errors or measurements, I use the word equivalently, distribute themselves in different ways. Okay. In some instances, they tend to bunch up in a particular place. Other instances, they tend to fall within specific bounds. Okay, and depending on the way that they distribute themselves, then a different type of probability distribution governs the occurrence of these measurements. So a Gaussian probability distribution governs the occurrence of these measurements or errors. A uniform or rectangular distribution governs the occurrence of these errors. Okay, so that's all the statistics that we need. Actually, we don't need anything more. So what should you remember? Repeated measurements, average, standard deviation. The average is the best estimate of the measurand that I'm trying to determine. The standard deviation is an indication of the dispersion and hence the uncertainty of my repeated measurements. Okay. Repeated measurements tend to follow different types of distributions, dispersions. Okay. The two most common ways that repeated measurements are distributed are either normally, so there's a bell curve which governs or shows you what the occurrence of a measurement or error might be, or following a uniform or rectangular distribution. So there are definite bounds within which you expect to find measurements or errors. Okay, that having been said, then we want to move on to see, well, how would we start to go about to estimate what are called standard uncertainties. So far, I haven't said anything about a standard uncertainty. I've talked about a standard deviation, and the GUM really does not distinguish between standard deviations and standard uncertainties. They're considered to be the same thing, okay? So a standard uncertainty is a more general way of talking about the dispersion of measurements. And general in what way? Well, because there are instances where I cannot repeat my measurements. So when I can repeat my measurements, then I can talk about a standard deviation. But there are cases where measurements cannot be repeated. This might not be so evident in a calibration lab, but imagine that you're doing a physics experiment in a large particle accelerator, and you have one chance to actually do an experiment and get some measurements. But you have to have an uncertainty estimate on the result of these of your experiment. So you have to have a way of determining the uncertainty associated. You cannot repeat, so you have to have a way. In this case, you cannot calculate a standard deviation from repeated measurements, but you can make certain assumptions and calculate a standard uncertainty which plays the role of the standard deviation. So really, uncertainties and standard deviations are different names to talk about the same thing under different circumstances. So standard deviation, the case where I have repeated measurements. Standard uncertainty, the case where I cannot repeat my measurements, or I don't want to repeat my measurements, but I still have to make some kind of an estimate of the uncertainty of the result of my measurement. Okay, so when I want to try to estimate my standard uncertainty, what are the basic steps that I have to follow? So first I have to identify the sources of uncertainty. So that means the sources of error, and see how much uncertainty those sources of error actually contribute, okay? Which is the second step. Estimate the size of the uncertainty from each source. So first I have to identify my errors and hence the uncertainty sources. Second, I have to identify or estimate how large the uncertainty that is coming from each source is. And finally, I have to some way combine all the individual uncertainties from the different factors that affect my measurement results to give an overall final figure. Okay, so these are the basic steps. First, identify the sources. Second, estimate how large they are. Third, combine. So it's fairly simple. There are situations where it can become a little bit harder. For example, you might have sources. So let's say that you're measuring, for example, length, okay? And we know that length is very much dependent on the temperature at which my measurement is being done. So one uncertainty source when I'm measuring length might be coming from the actual instrument that I'm using, from the calibration of the actual instrument that I'm using to measure. And the second source might be from a thermometer which is being used to measure the temperature, so I can make corrections for any contraction or dilation that the item might have because of temperature changes. So the uncertainty of length will have units of length. The uncertainty of temperature will have units of temperature. So when I combine these uncertainties, I better make sure that I'm combining things which have which are similar. Okay, I can't combine length with temperature, so I have to make sure that I find what the equivalent contribution to length uncertainty, a temperature uncertainty might be in that particular instance. So there are issues of that sort. for someone to contend with. But other than that, the process is fairly simple. Identify the sources, estimate. So the metrologist is responsible for doing this, for identifying the sources because you know your measurement, identify what the contribution of each source is because you know your measurement, and then it's a matter of simple mathematics to combine these things to find the uncertainty of the overall result. Okay, so this is something that I already discussed, told you about. I think I jumped the gun here. The fact that a standard uncertainty is basically the same thing as a standard deviation. So this is what the slide says in reality. So why is it called standard? Because it's expressed at a particular level of confidence, okay? And this particular level of confidence is about 68% when we're talking about a normal distribution, okay? So standard deviations, standard uncertainties, the word standard in front of them means that they are standardized to a particular level of confidence. So that's another thing that I have to be careful about when I'm combining uncertainties. I can't be combining uncertainties which they're not referred to the same level of confidence, to the same probability. Okay, I cannot combine a 68% uncertainty with a 95% uncertainty and with a 30% uncertainty. So I have to make sure that when I'm combining, everything is referred to the same level of confidence. And this is what the standard in front of the word uncertainty and deviation actually mean, that these are standardized. Okay, well, so there are two approaches to estimate standard uncertainty. Remember I said previously that there are situations where I can repeat my experiment and I can have repetitions, but there are also situations where I need an uncertainty estimate, but I cannot repeat my measurements. I brought the example of a physics experiment, but even more down to earth is the weather. So when someone is trying to predict the weather, they say, well, I will forecast this much of rain, 45% within the next 3 days. Well, that's an uncertainty estimate there. But obviously the weather cannot be repeated. So you make measurements and you use those measurements in order to forecast something, okay? So you have to have another way of estimating uncertainty besides these repeated measurements. And this other way is really by using all of the available information that someone has in order to estimate the margin of doubt that he has about the particular measurement that he is making. So depending on whether I estimate uncertainty through statistics, through repeated measurements, or I estimate uncertainty through any other means, then I talk about respectively type A and type B evaluations. So that's the only difference between type A and type B, okay? In the past, type A was associated with random errors. It was called a random uncertainty, maybe in some instances. Type B is systematic, but there's no one-to-one correspondence between these. So a type A uncertainty might be a systematic, due to systematic errors, or it might be due to random errors. Sorry, a type B might be to systematic or random errors. A type A is always due to random errors. So there's no one-to-one correspondence. Right. Nowadays, pretty much, there's no clear distinction between. It doesn't really matter. So here for type A, as I said, you use statistics, so you use the average and the standard deviation. For type B, there is no standard deviation, there is no average, only one measurement. So you have to use all of the available information and convert this somehow into an uncertainty value. So what might all of this information be? It might be based on past experience of this particular measurement. It might be information that's contained within a calibration certificate or manufacturer specifications. It might be from specific calculations, tabulated calculations, published information, or common sense or engineering common sense, I should say. So any information that I have, I can use it in order to provide an estimate for uncertainty. Okay, well, how do I evaluate standard uncertainty of type A? So when I have a set of repeated measurements, we've talked about this. I take the mean and I estimate the standard deviation, and then the standard uncertainty is the standard deviation of the mean or the mean error. So that's just the estimated standard, so it's the estimated standard deviation divided by the square root of the number of measurements. Simple. So type A uncertainty and mean error or standard deviation of the mean are the same thing. And that's that. That's all the statistics that someone needs in order to do type A uncertainty estimations of repeated measurements. There are other types of measurements that fall under this category, so of type A. Another common situation is when I have a number of measurements, but they differ depending on some kind of variable. So for example, I might have the position with respect to time. And in that case, I might be interested to see what is the best function, the best curve that relates the position with respect to time. And I typically can do that by doing what is called a least squares fitting, okay? And I can estimate how well I can determine how well I have estimated the curve that describes this variation of position with respect to time. The estimation of how well, the uncertainty, I've estimated the curve is a type A also uncertainty calculation. There I don't have repeated measurements, but I have a number of measurements of the same measurement under different circumstances. So if I take this into account, I'm pretty much talking about something which resembles the repeated measurements. So I won't talk about that today, but during the next session of this, I will have something to say about using least squares to estimate the best curve to describe a number of measurements. Okay, so how do I evaluate type B standard uncertainty? So you need to know, you need to have some information, okay, and then you have to assume a particular type of distribution which governs the spread, the dispersion of the measurements that you're considering, the type of measurements that you're considering. So if it's possible to estimate an upper or lower limit of error, okay, that's the information necessary, then you might be able, or it's the best way to account for the dispersion is to assume that it's equally likely for a measurement to fall anywhere between this upper and lower limit of error. So the information available are upper and lower bounds of error or measurement. And the assumption that you make is that there's no particular reason why these measurements should bunch up somewhere. It's equally probable for them to show up anywhere between these bounds. If that's the assumption that you make, then the standard deviation can be found by dividing the half of the interval within which the errors or measurements are expected to show up by the square root of 3. So the semi-range between the upper and lower limits divided by the square root of 3 is a type B uncertainty estimation, okay? And in fact, it's an uncertainty estimation where a rectangular distribution has been assumed for the spread of the measurement within these bounds. Okay, so graphically, this might look something like this. So on the horizontal axis, sorry, on the horizontal axis, I have the errors or the measurements. You see where the bounds are, x minus a and x plus a. This interval is centered around the most probable value, okay? And this is a representation of a rectangular distribution. So within these bounds, the measurements of x will be equally probable, and the uncertainty associated with this type of a rectangular distribution is given by this expression here. So it's half of the interval divided by the square root of 3. Is this clear to everyone, or do you need some clarification?
Can you repeat for me why you select 3? Why it's 3 and not 2 or not more than 3?
Yeah, because that's the way. I don't want to go into it because it takes some math to prove this, but the square root of 3 comes along with the rectangular distribution. So it can be proven mathematically why this is square root of 3 and it's not something else. But I don't want to do it right now. I mean, how can you do it, though, if you're interested? Well, the assumption is that all of the measurements fall within these limits. So then the probability of a measurement, any measurement, to be in here is equal to 1. So it cannot be outside. So the probability of a measurement to be in here has to be equal to 1. And what's the probability? Well, it's the area under this curve. So if someone calculates the area under this rectangle and equates this to 1, then you will see that this number, the square root of 3, pops up. Okay, so I don't want to go into the mathematical details of this. There are other instances for other types of distributions where it's not square root of 3, it's something else, and we will see one in just a minute. Okay, so the square root of 3 is associated with a rectangular or uniform distribution. Any other question?
Yes, Doctor. Can you give us an example on the source of type B uncertainty? Like what it come from, where it come?
Well, it can come from anywhere. It's not
Just
that the uncertainty is coming. I mean, you could have a type B uncertainty if you have limited information. Okay, so if the only information that you have is that your errors are between an upper and a lower limit, then a good starting point for an assumption of a distribution of errors is a rectangular distribution. So if you have the minimum amount of information about your errors or your measurements, you assume a rectangular distribution. Does that answer?
Yeah, we need just to assume that it is a rectangular. Yeah.
Yes. Remember, when we're talking about type B evaluations of uncertainties, we basically have a piece of information and we convert this information into an uncertainty by dividing it by something. Okay? What is this thing that you divide it with? Well, it's determined by whatever assumption you make about the errors that you're talking about. So it's a matter of the errors. It's not a matter of a particular type of measurement. So we can be talking about any type of measurement, but it has to do with the errors and the amount of information that you have with regard to this, to these errors. So if the only information that you have about these errors is that they are within certain limits, then it's reasonable to assume a rectangular distribution.
Doctor, is the uncertainty of measuring in standard, which is coming, from this certificate of calibrations, considered type B? I mean,
yes,
when
it's considered type B. Well, it is because you're using the information on the certificate, which is an interval, really, a number, a parameter, which is the expanded, it's the uncertainty, and you have to divide it by something in order to convert it into a standard uncertainty. So that's also a type B calculation. Okay, so the use of information from wherever, from discussions, from books, from certificates, from the internet, all of this is information. Okay, so how much someone, if that's reliable information or not, that's a different issue. But using information in order to determine the amount of doubt that you put in a particular measurement, that constitutes a type B evaluation. So let me give you another example. Maybe this this clarifies things a little bit. So remember what the assumption here was. The assumption was that errors fall within two limits, and they're equally probable to fall anywhere between these two limits. Okay, this means that these errors are governed by a rectangular or uniform distribution. Let's look at a similar situation where again we have bounds. Okay, however, for some reason I put more I put additional information here, and I say that I expect most of my errors to be close to the center of this range. Okay, so this is additional information with regard to the previous case. In the previous case, we had bounds and nothing else. Here I have bounds and the expectation that most of my errors will fall near the center. Then I can assume a triangular distribution of my errors. And in that case, I have again the half width of the interval But now I don't divide it by the square root of 3, I divide it by the square root of 6. Again, this number can be calculated, but that's beyond this this presentation. Okay. So what's interesting here? It's interesting that depending on the assumption, rectangular or triangular, the uncertainty becomes smaller. So same width A, it's in the rectangular case, it's divided by the square root of 3. Here, it's divided by the square root of 6, so the uncertainty is smaller. Okay, the A is the same. The error, the expected errors are the same. The assumption of the distribution is different. That makes the uncertainty smaller. Is that reasonable? Yes, because in this case, I am using more information. I am using the additional information that my errors are close to the center. So the more information that I put into my system, the smaller I expect my uncertainty to become. And this is what we've just seen here. Rectangular distribution, nothing except bounds. Triangular distribution, bounds plus expectation near the center, uncertainty decreases. So then the graphical representation of such a distribution would look something like this. Definite bounds, larger probability of or expectation, let me say expectation, larger expectation of values or errors appearing near the center. This is what this, how it can be represented graphically by a distribution. Is this understood? So the assumption of a distribution is not associated with any type of measurement. It's associated with what my feeling is about the particular measurement. It's associated with the amount of information I have or the amount of doubt that I have. So it's kind of subjective, okay, about this particular measurement.
Doctor, the normal practice, are we considering that in our estimation of the uncertainty? Or we
What
can,
do you mean normal practice?
I mean, this is it gonna be, it might, you know, because I have seen that, oh, this is, it can be neglected. Is that, you know, normal practice?
You mean that some components, some errors might be negligible?
Yes.
You don't take them into account?
Yes.
Yeah, that's a different issue. That has to do with that has to do with my original what I was talking about, how to estimate uncertainty. So you have to estimate, you have to identify the sources, and then you have to provide estimates of how large these are. Mm-hmm. So if then one is 10 times smaller than the other, well, you will not be making a large mistake in uncertainty if you neglect the one that's 10 times smaller. Okay? It all depends on how accurate you want to be.
Doctor.
Yes?
Yeah, among the three distributions, the Gaussian, the rectangular, and the triangular, the rectangular is giving the higher uncertainty. So if we have a doubt about the which one are we going to use, it's better to use the rectangular distribution because it's better to overestimate the uncertainty instead of underestimating it. So in the calibration, we use the most one that we use is the rectangular distribution.
That's correct. However, you have to always keep in mind that, okay, that's, let's say, like the easy way out, because that's true. What you're saying is 100% true. However, you might be not doing justice to the instrument that you're calibrating, because the use of the rectangular distribution might be a shortcoming of your capabilities and not of the instrument itself. So if that's not the case, then I agree 100% with what you said. But someone has to be careful, huh?
Thank you. Thank you. That's true.
Any other question? Omar, I'm sorry, I lost the time. I don't. Where are we in terms of time?
We are in a good shape. Continue.
Okay. So you let me know, right?
Yes, I will.
Okay.
I think we will break at 1 o'clock. I think it's our.
1 o'clock. It's sorry, it's 12 now. Okay. All right. So to summarize, I've talked about how to estimate standard uncertainties. There are two ways of doing it, either by using standard deviation statistics or because of the knowledge of my measurement, assuming some kind of a distribution of my errors. Usually, this would be using the assumption that they fall within definite limits, and that's pretty much it. If I don't have any other indications, okay, of something. Okay, well, the next question then might be, and the third type of estimation, type B, is by using the calibration certificate. I'll have more to say about this in a little while, but since it was brought up, I can use the calibration certificate uncertainty, and dividing it by the appropriate number, I can use it to estimate a standard uncertainty. Okay, so these are, between these three situations, certificate, type rectangular and triangular, you have, for typical calibrations, you have more than 90% of the situations, of the cases covered. Okay, so the next step then, if you remember, first it was to identify the sources of uncertainty. Second, to estimate how large they are, the uncertainties. Third is to combine. So let's see how we can combine uncertainties. Irrespective of the way that they are calculated, they are combined by summing in quadrature, or otherwise known as a root sum of the squares. So you cannot just combine them algebraically, but you have to square them and add the squares and take the square root of the sum of squares. Okay, this will provide you an estimate of the combined standard uncertainty. Several comments I can make about this. Firstly, my note down there, if you do something like this, then you have to make sure that all of these components have the same units. You cannot be combining apples with oranges. Okay, so all of these uncertainties, when you do this, have to have the same units. There's a systematic way of accomplishing this, and I will talk about it in just a bit. But other than that, it's simple. So in essence, what you're doing is you are summing variances, not standard deviations, but variances. So you're not summing standard deviations or standard uncertainties, but the squares of those things. Again, this is the typical way of doing it. There are exceptions, which I will just mention right now. I will not talk about them, but there are situations where you might need to add uncertainties instead of the squares of the uncertainties. And this is the situation when errors are not independent of one another. So when errors are correlated, then you cannot just blindly say, well, I'll square and I'll add. You have to think about it a little bit more. But I won't go into more detail, at least today. Okay, there are two simple situations which one considers when combining standard uncertainties. One is when you have addition or subtraction of quantities. Okay, so for example, if you want to find the uncertainty of the total length of a fence, which is made up of different width fence panels. Okay, so you're adding up lengths here, and each one has an uncertainty associated with it, the length of each panel, fence panel, and let's assume that they have not been that they are not correlated. The errors are not correlated, to make things simple. So in this case, then it's very simple to determine the combined standard uncertainty, because it's just this root sum square addition, okay, that I mentioned. So simple case, if I have the addition of things, then the uncertainty is calculated by this expression here of the composite result. So yeah, there's nothing more to say here, I think. Another easy situation is when I have multiplication or division. So if I have multiplication or division in order to determine a final quantity, for example, if I want to find the area of a rectangular carpet, which is then the length times the width of the carpet, then I cannot add the uncertainty of the length, the square of the uncertainty of the length, and the square of the uncertainty of the width. However, I can add the squares of the relative uncertainties of the length and the width. Okay? To find, of course, the relative combined standard uncertainty. So between the addition of things to find the final result and the multiplication of things to find the final result, again, in calibration, you have, at least for physical quantities, you have maybe 80% of the situations. Okay. I think it's simple enough. So here you add the squares of percentages to find a percentage of a combined standard uncertainty. Here you add the square of values, of uncertainty values, to find a combined standard uncertainty. Any question? Note that all of these things have the same units. So this is true if everything has the same units. If they do not have the same units, then you cannot do this. But as I said, this is about 80% of the situations that you will come across in physical metrology, at least.
I have a question. In the next,
Yes.
in this example, the area is area's unit is different than the width and length unit, right? So
No.
how the area is
No, but
square? Like
the area is the end result.
Okay,
So
okay.
I'm trying to find the uncertainty of the area, but these things have the same units.
Okay.
Well,
okay.
In fact, let me rephrase now. You brought up an interesting point, because here you don't have units. These are relative values. So these are percentages. Okay. So here you're adding percentages. Right? This is an uncertainty divided by of the length divided by the length. So there are no units here. No units here either.
Yeah.
Okay. However, here there are units, and you have to make sure that A, B, and C have the same type of units. They're measured in the same units. It can't be time, let's say, distance, and mass. Okay, they all have to have they have to be, uncertainties of the same quantity. Otherwise, you cannot add them. Here, it's not important because these are relative values. There are no units associated with them. These are just percentages.
You
Okay.
mean you divide it by their unit to cancel the unit?
Yeah, there are no units here because uncertainty of length is, let's say, in meters, and the length is in meters. So
So it
this
cancel
thing
each
here
other.
has no units.
Okay.
Correct?
Yes.
Okay. Okay. All right. Okay. So, and that's pretty much it. So you've determined now, if you're at this step, you've already determined the combined standard uncertainty. So that's the combination of all of the uncertainties that are relevant to your problem. Now, there's one more issue, that this is a combined standard uncertainty, standard. This is a combined standard uncertainty. And standard uncertainty is usually designated by the lowercase u letter. A standard uncertainty under the assumption of a normal or Gaussian distribution means that there is a level of confidence of 68% approximately. Now, if for some reason you want to make this level of confidence larger, so you want to increase the probability associated with finding the true value within that interval, then you have to expand your uncertainty. You have to talk about an expanded uncertainty. So in other words, if you want to increase the probability of finding the true value within the interval, you have to make the interval larger. So how do you make this interval larger? How do you expand the uncertainty? It's very simple, because you multiply it by what is called a coverage factor. So a standard uncertainty is at a probability of 68% under the assumption of a Gaussian distribution. If, for example, you want to make the probability 95%, then you have to rescale the interval, expand it, by multiplying it